let's have a look at this, right? Because I think you guys have already started talking about, when we're talking about multiplying numbers in a particular way, for example, without replacement, we saw that they were decreasing each time. And we want to think, is there a better way that we can do this rather than typing it out? And you've seen this button, and you've even used the terminology, right? What's it called? It's called a... Exclamation mark. It's called an exclamation mark, just like in English. When you do, let's just look at what happens with these numbers, right? 1, and it's actually called factorial, okay? When you do say it though, you have to say it like you're really excited. It's like 1. That's how you have to say it. So this is 1.
1 factorial.
Okay, what does that give me? It gives me, okay, 1. That's not particularly interesting. Let's go again. Let's go.
2.
Yeah, let's go 2.
2 is 2.
It's 2.
It's 2.
Next one is 6.
0 is 1. 6.
Can you guys calculate the next for me? What's 3 factorial? What's that? What's that going to be? What's 3 factorial? Let's keep going. 4 factorial.
24.
Is it 5?
5 factorial.
Yeah, then it's 100.
Oh, it is 120.
120. Okay, now. Do you think you know what's happening here? Why am I getting these numbers? Where are they coming from?
5 times.
Oh, basically you're descending in...
Okay, this is just 1.
So 5 would be 5 times 4 times 3 times 2 times.
So it's 5 multiplied by all the numbers down to 1. Okay. So what's this? 4 times 3 times 2 times 1. 3 times 2 times 1. I agree with these. 2 times 1. And what? That's just 1. Yeah. What if I go 1 more? Wait, so 0 factorial. Put that in for me. What was that?
1.
What? What do you mean it's 1? Put it in for me.
It is.
It is 1.
Yeah.
What? But I thought you said we were saying this number, factorial, is all the numbers multiplied by going descending order until 1. How does that one make sense?
It's like the combination of like things with 0.
Minus 1 factorial is minus 1.
Because 0 equals 1, because 0 is equal.
Okay, we'll come back to this one. Okay, I want you to park that
That
thing.
doesn't make sense, then 1 should be 2.
Now, there is an informal definition of how we describe factorial notation, and it is this. We can say that n factorial is equal to, if we think about numbers going down, right, I'd start with that number, then what happens? I have to multiply it by the number less than that. What's the number 1 less than n?
N minus 1.
N minus 1. And then you can have
0,
n minus 2,
1.
n minus 3. I'll talk about 0 in a moment. But then we have all the way down to 1. That's an informal kind of definition of factorial notation. Can you write that down for me?
Yes.
Why is this particularly useful? Because if we think about our counting techniques, if we're thinking about, alright, how many different kind of positions there are and how many different choices there are, these numbers can be quite large. Let me give you an example. A deck of cards. How many cards are there in a deck of cards? 52.
What about the jokers?
We take the jokers out. Don't like the jokers. Now, I have 52 cards. If I want to think about how many different possible arrangements I can have with this, how many different ways I can deal this out, right? How many different spots are there? There's 52, right? Because if you think about it, you're saying, okay, how many choices do I have for the first card that I'll give you? I have 52 possible ones. I'll give that to you. How many possible ones do I have for the next one? I have 51, right? And I do this until I've dealt out all the cards. And that's 50 multiplied by all the numbers down until I reach 1. So you can see how this notation is very powerful, right? You don't have to now actually calculate or even write this all out. You can literally put into your calculator what is 52 factorial, and that would be the arrangements for the number of deck of cards. And how many different ways we can deal that out, okay? All of those cards, right? 52 factorial, just out of curiosity, what is that? It is a big number. The number's so large that they have to use scientific notation. I think we're pretty bad at kind of judging like how large numbers are. Okay, I know this is 8 point something times 10 to the power 67, 10 to the 67, 67 zeros, right? Like, what does that even mean? I'll give you a little bit of an analogy. if we were to go to the beginning of time, from when the universe started, and we got not just one person, but we got like every person in the world, let's just say 7 billion people, and they were all shuffling this deck, and they're all dealing out these hands every single second somehow, we would not be anywhere near close this number at all. And you can find that out yourself. But it just makes crazy how to think like how big this number actually is, right? 52 factorial, it uses scientific notation, and like it's something that we can even find. It's such a large number that it's possible that if I shuffled this deck right now and dealt them all out, that kind of arrangement has never been dealt before in the history of the universe. Like that's possible. It's not impossible, but it's definitely possible, right? Let's look at another one. What about this? Let's make this a smaller number so I can actually understand them a bit more.
So do you just leave it as
Yeah, we leave it as 52 factorial because it is far too large. What about this? When I'm doing these, notice what's happening with the situation, right? I've got 52 cards, I'm dealing 52 out. I've got 12 jerseys, I'm giving them to 12 students. And I'm applying this kind of situation to everybody there, okay? So the factorial notation, we don't want to just use it willy-nilly. We kind of want to think about, all right, what are my spots still? Here I still have 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then I've got 12 jerseys I can give out. I've given out one. There's one less I can give out. There's 11, and there's 10, and so on and so forth. So you don't want to just kind of think about, oh, I can see that there's like a certain number of things giving out, I can just put that in factorial, because you guys tried to use that with an example before and it didn't quite work out, right? Because sometimes factorial notation isn't the tool we want to use to solve these problems. It's only in the situation where, I suppose, if you're thinking about, let's go back to the deck of cards, right? I'm actually handing out every single one of those cards. If I was only interested in like a hand of 4 cards, right, I can't use that. Does that make sense? Right? Because I'm using up all of these slots here. So that's something you want to think about when you're trying to use factorial notation. In this case, I can use it. For part A, it's just going to be 12 factorial. What's going to happen with part B, though, if I reserve my favorite number?
What?
If I reserve my favorite number, what's going to happen? How did you get that?
Because you picked one out.
Yeah, so if you think about it, right, I go up to and say, no, look, I like the number 5. I want the number 5 here. That's mine. Essentially, what you're doing is, you're taking out one person, you're also taking out one jersey, so we get rid of that, and then what's left? It's just 11 factorial, right? So that's part B. Think about arrangements of a word here, right? If you think about maths, right, there's 5 letters there. And again, I'm thinking, oh, okay, let's assign it. I've got how many choices for the first one? Well, there's 5. But once I've used that letter, because they're talking about arrangements of this word, it's not like I can just keep using M over and over again, right? I've used that M or something, and then I've got, what, 4 left to choose from, right? And then I've got 3 left to choose from, and then so on and so forth. So you can see how that uses that factorial notation there, right? So this would just be 1, 2, 3, 4, 5 factorial. What about friends? What would that be? 1, 2, 3, 4, 5, 6. Yeah, it's just the number of letters that there are. 7 factorial, right? Easy. How many people in this room? 1, 2, 3, 4, 5, 6, 7, 8, 9. You didn't include me.
Oh.
There's 9 people in the room, 9 spots. I'm arranging them in a row. That would be 9 factorial. What if I'm on the left? I have to be on the left of our row. Yeah. So I've got my 9 spots. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yep. So usually it'd be 9 times 8 times 7 all the way down, 3 times 2 times 1. But yeah, if I have to be on the left, I'm just kind of taking that out. I've got this seat that I reserve. Okay, I have to be there. That would be 8 factorial.
Yeah, that's why we put 8 there, because we still
Can I do another restriction? Now, you know in movies, right, I hate being on the end because then you can't talk to people. You're just like by yourself. Like, oh, hey, there's no one there. Okay. You know. So, like, I don't want to be on the end here, right? So here's my positions. I don't want to be on the ends. So what number of choices do we have for each selection? Because you're going to see more restrictions being applied here, right? if you come back to this idea of drawing these lines and think about how many choices you have for each one, that's going to help you out. Think about it, right? We've got 9 people in total.
So the first one will be 8. Can't be on the end.
Okay, I can't be in the end. I'm picky. No, I'm not going to sit there. Only 8 people can go there.
Is 8 still an option for the second one?
Is 8 still an option for the second one? Why is that? So let's think about what's actually happening here, right? We have 9 people in total, and someone's taken a seat. But remember, again, right? There's only 8 people actually that can take that first seat because I can't sit there. I don't want to sit there.
Yeah, so there's 8 left that can take the next seat.
Because I'm still here.
Yeah.
Right. Okay. That's one idea. Yeah. Can you see how that works? Yeah. Yeah, it would still be 8, right? Or another way you can think about it is let's do the conditions first. If I don't want to be on the end, let's look at the other end. How many people can sit there?
8.
Well, I don't want to be there. There's only 7. Does that make sense, right? Because 8 people can sit there, right? That's one person who's already sat down. Now there's only going to be 7 that can sit in this one. And then what? Then I've got how many people left overall? 7, right? Can you see that? Because we start off with 9 people. Yeah, it's a bit strange, right? We start off with 9 people, okay? And I'm saying, I don't want to sit there. So I'm out. There's only 8 people that can go there. There's only 7 people that can go there. And then I'm back in. And now we have 7, 6, 5, 4, 3, 2, 1. And you can see that it works out with the numbers, okay? And we can still multiply them all together. A far easier way to write that would be, well, we've got, what's this here? That's just 7 factorial. So it would be 8 times 7 times 7 factorial. Okay? So even though we apply some restrictions here, can you see how helpful just drawing this out can be, right? It just helps you get a visual sense of what's actually going on, right? Last one, a 10-digit password without repetition. So a 10-digit password without repetition, and we're only using the digits 0 to 9 here. So you've seen this, you've seen this without repetition means, right? So if I have my 10 places, 1, 2, 3, 4, 5, 6, 7, 8, 9. I wonder what it could be. 10 for the first one, but then I've used it, then I can't use that same digit again. So it's going to be 9, 8, all the way down to 1, right? Or 10 factorial. 10 factorial. Are we going to do one with circles? Why would circles change things? I don't know. Why don't you go and have a think about it? How would circles change things?